For decades, Pluto existed in our astronomy books as a stubborn mystery, a tiny, blurry point of light sitting billions of miles deep in the cold storage of our solar system. This diagram maps out the classic 20th century view of our neighborhood. We had the neatly arranged rocky inner planets near the Sun, followed by the massive gas giants. Pluto, however, defied this order, carving an eccentric path that crossed straight through Neptune's orbit. The puzzle of that orbit traces back to 1930. A 24-year-old named Clyde Tombaugh, fresh off a Kansas farm, spent thousands of hours scanning glass photographic plates in Arizona, looking for a single speck of light that moved against the fixed stars. His tool for this discovery was a large, homemade wooden Newtonian telescope built from leftover farm equipment. His crude telescope gave us a coordinate in the sky, but answering what Pluto actually was meant sending a camera across an unimaginable void. That single point of light sparked an 85-year scientific relay race to the very edge of the Sun's reach. By 1989, the clock was running out. A fringe group of passionate young scientists, who called themselves the Pluto Underground, realized Pluto's orbit was carrying it farther from the Sun. If they didn't launch a probe soon, its thin atmosphere would freeze solid and collapse onto the surface before anyone could study it. Ground-based telescopes couldn't penetrate the distance, and even our finest orbital tools were hitting a hard limit. The Hubble Space Telescope could only resolve Pluto as a highly pixelated blob. We knew it had a contrasting surface of bright and dark patches, but there was zero geological data. To get that data, the Pluto Underground spent 15 years pitching missions. They faced endless competitive reviews, severe budget cuts, and institutional skepticism. Plans for the Pluto Fast Flyby and Kuiper Express were repeatedly greenlit, then abruptly canceled. Building a rocket is an engineering problem. Securing the political and financial runway to keep a mission alive through multiple presidencies requires intense, bloody-minded persistence. When NASA finally approved the New Horizons mission in 2001, the team had to solve a brutal physics equation. To reach Pluto before its atmosphere collapsed, they needed to pair an ultralight payload with the absolute largest launch vehicle available. The resulting spacecraft was a marvel of miniaturization. It carried 7 powerful scientific instruments, all engineered to survive the deep freeze of the outer solar system while drawing less power than half a standard 60-watt light bulb. That featherweight probe sat on top of an Atlas V rocket, heavily tricked out with solid rocket boosters to maximize thrust. The launch in January 2006 shattered human speed records. New Horizons passed the orbit of the Moon in just 9 hours, a trip that took the Apollo astronauts 3 full days. But raw speed couldn't erase the geography of the solar system. Even after catching a massive gravitational speed boost from Jupiter, the probe still faced a 3 billion-mile stretch of empty, featureless space. To protect the delicate instruments from wearing out over a 9-year transit, operators placed the spacecraft into a deep electronic hibernation. Back on Earth, the engineering team settled into a grueling waiting game. For years at a time, their only connection to the probe was a weekly automated ping from the darkness, confirming the systems were still alive. This massive time delay extracts a heavy human toll. The young men and women who designed the mission in their 20s and 30s knew they would be a decade older, deep into their careers by the time the probe finally reached its target. Inside these mission control rooms, operators meticulously rehearsed the encounter sequences for a flyby that was still millions of miles and several years away. We often measure space exploration in thrust and trajectory, but navigating the outer solar system is equally a test of psychological endurance. Surviving the wait demands absolute focus. In 2011, that focus was tested. As New Horizons closed the gap, astronomers using Hubble discovered a swarm of tiny, previously unseen moons orbiting Pluto. These tiny moons have almost no gravity. Any micrometeorite impact kicks up dust, surrounding Pluto with an invisible debris ring. At New Horizons' tremendous speed, hitting a rice-sized particle would strike with the force of a bomb, shredding the electronics. The team scrambled to calculate a backup flight plan, known as SH-BOT, Safe Haven by Other Trajectory. This Hail Mary maneuver would force the probe to steer much closer to Pluto, aiming for a zone where the planet's atmospheric drag had cleared out the dust. Decades of design, political fighting, and 9 years of silent transit came down to one critical calculation. The team had to steer blindly through a cosmic minefield, where a single millimeter error meant total mission failure. On July 14, 2015, New Horizons hit its tiny 100-kilometer target box flawlessly. It woke up from hibernation, executed its pre-programmed twists and turns, and phoned home to confirm it survived. Astronomers expected to see a cold, dead rock, heavily scarred by billions of years of asteroid impacts. Instead, the data revealed a world that is still geologically active today. The surface was completely clear of old craters. It featured towering ice volcanoes, vast glaciers of nitrogen, a multi-layered atmospheric haze, and regions stained deep red by complex organic chemistry. Geologists had long assumed Pluto was too small and too cold to maintain an internal engine. These images of active nitrogen glaciers prove that even at the edge of the solar system, planetary bodies can remain geologically alive for billions of years. The data from the flyby confirmed that Pluto serves as the representative for a massive, previously unexplored region of the solar system. This map outlines the Kuiper Belt. It is a massive, donut-shaped third zone of our solar system, holding hundreds of thousands of icy dwarf planets and ancient comets. Because they orbit so far from the sun's destructive heat, these objects are untouched. They are primordial ingredients, deep frozen records of the material that formed our entire planetary system 4.5 billion years ago. Processing the mountain of data pouring out of this third zone is now falling to a new cohort of postdocs. These are scientists who were sitting in high school classrooms when New Horizons originally launched. This 85-year relay, from Clyde Tombaugh's glass plates to the digital sensors of New Horizons, has become a living legacy. These missions outlast the careers of the people who start them, proving that our reach into the deep solar system is defined not by the speed of our rockets, but by the generational stamina required to see the journey through.